I know USACO's over, okay? I know, but like, I can't stop myself, dude. USACO is just too addicting. It's more addicting than Minecraft, okay? Like, if it was less addicting, I would be playing Minecraft right now, but you gotta know. USACO turns on my dopamine receptors real good, okay? Hello everybody, I'm Karar, and today we're going to be walking through the USACO 2020 January Contest Silver Wormhole Sort problem. And the reason I'm doing this problem is because I was looking through the comments and two of you guys commented that you guys wanted to see this one done, and I think it's an interesting problem from what I've heard, so we are going to do it. But before we go any farther, USACO is over, okay? I understand that. So we can't hold on to the past, okay? So we gotta move on. So basically this video is more of like a filler while I think of what other stuff to do now that all the Olympiads are canceled. If there's a specific Olympiad or thing you want to see, just let me know down in the comments. I have seen your guys' comments. One guy wanted a Science Olympiad prep thing. Other people, well, honestly, most of you guys just wanted USACO videos. God dang it, guys. You guys gotta give me more variety. No, I'm kidding. But another thing that is coming up are AP tests. So what I'm thinking of doing is just doing some AP like class reviews just before the test. So put in the comments the AP that you like best, first come, first serve. Actually, I don't know how I'm going to do it, but put your APs in the comments. I'll see which APs I want to do reviews for. Okay. Well, that's enough talking. I'm sorry. Let's get into the problem. Let's do it. Okay. The Farmer John's cows have grown tired of his daily request that they sort themselves out before leaving the barn each morning. Understandable. I would be fed up too, okay? They have just completed their Bruh. Okay, that I have not done. Dude, what's the point in working on Olympiad if cows have already gotten PhDs in quantum physics? What the heck? And are ready to speed things up a bit. This morning, as usual, Farmer John's and cows, conveniently numbered 1 through N, are scattered throughout the barn at N distinct locations, and also numbered 1 through N, such that cow I is at location PI. But this morning, there are also M wormholes, numbered 1 through M, where wormhole I bidirectionally connects location AI with location BI and has a width WI. At any point in time, two cows located at opposite ends of a wormhole may choose to simultaneously swap places through the wormhole. The cows must perform such swaps until cow I is at location I for one is okay. The cows are not eager to get squished by the wormholes. Help them maximize the width of the least wide wormhole which they must use to sort themselves. It is guaranteed that it is possible for the cows to sort themselves. Okay. Alright, so basically your input gives you N and M, and then it gives you the order of the cows, and then it gives you a bunch of wormholes. Yeah, so it gives you the start point, the end point, and the what's WI width. Wait, what? What does the width do? Oh, so the width is just like how big it is, so they just want to use the biggest. No, what? Maximize the width of the least wide worm. Wait, what? Oh, okay, so they want to use the biggest wormhole they can. Okay, so basically they want to use the widest wormhole that they can. So basically, like, I mean, we have 1,000, m is less than or equal to 1,000, so we could do n squared because 1,000 squared is only 10 to the 6th. Alright, and then basically the way it works is that, like, if you only need these two wormholes, then it's fine. Okay, and if they don't need any wormholes, just output 1. Okay, so basically what we got is we got our array of cows. B. Now we can draw. Okay, so 3, 2, 1, 4. Epic. And then we have something connecting 1 to 2 with 9. We have something connecting 1 to 3 with 7. Something connecting 2 to 3 with 10. And 2 to 4 with 3. Okay. So basically, if we're allowed to use wormhole 9, then we're also allowed to use wormhole 10, because that doesn't change the maximum of the least wide wormhole. Okay, yeah, that's what we have to say. So basically, if you take the maximum of the least wide wormhole, if you take the least wide wormhole, then you could take any of the other wormholes and the least wide wormhole will not change. So for example, if the cows had to use like 7, that means it's okay for them to use 9 and 10, but even if they use 9 and 10, the least wide wormhole will still be 7 and we don't have to change anything. So why don't we just sorted the wormholes in order, right? And we just went through, like, let's say that we had to use 10 as a smallest wormhole. That means the only thing that could happen is that these two swap. And then, is that enough? No. Then we move on to 9, and we're like, oh, that works. So then we print out 9. So can we just do that? Wait, could they move from... Okay, so they can't... The only way they could swap is through wormholes. Okay. Well, okay, let's think about it this way, right? Let's say that, like, each position is like a node, right? Wait. So if we erase this. So let's say we have, like, this is position 1, this is position 2, this is position 3, this is position 4. And we have a wormhole connecting this, we have a wormhole connecting that, we have Well, okay, let's start from 10. So the first wormhole that we're allowed to use is 10. Let's say that that's a min wormhole. So that's the only wormhole we could use, and thus the only one that we could switch or move around are these two guys. And clearly, if we have 3, 2, 1, 4, we have to move around more than just these two guys, right? But if we connect this guy, because it's our 9, and that's okay, right? Because now, like, even if we have 3, 2, 1, we can make any permutation of 3, 2, 1 now that we've connected this. Like, okay, let's say we wanted to make 1, 2, 3. We swap the 1 and the 2, we swap the 1 and the 3, then we swap the 2 and 3, and then it's back to 1, 2, 3. Let's say we wanted 2, 1, 3. Then we swap this and we swap that. So we can make any permutation as long as these nodes are connected, like the position nodes are connected. So basically, what am I trying to say? So basically what we could do is we could go from the like last wormhole, the biggest, widest wormhole, and go keep adding smaller wormholes until we're able to sort it. And how do we check if we're able to sort it? Well, basically, like the numbers in these positions that are connected can't go to any position that's not connected by one of these edges. So we basically have to make sure that each number is connected to its position. And this is literally just a union find algorithm, and this is pretty cool. I think this is, whoa, that's actually so cool. Holy. Wait. I've never used union find in, oh, okay, fine. Union find is a pretty common algorithm, but I personally have not used union find in a USACO contest, so this should be fun. Okay. And do we even need to be smart about the union find? No, because we can literally do n squared times, so we can just do a stupid union find. Epic. So basically what a union find does is it basically keeps track of connected components, and like if you connect two connected components, it connects them. So the reason why that's cool is, let's say that you have like, I don't know, let's see. So let's say you have this edge and this edge. And right now our connected components are saying, oh, these guys are in one component, these guys are in another component. And then if we were to find another wormhole that connects like this, then our union find algorithm will automatically, for us, connect these two groups. And then we'll realize that all of these guys are now in the same group, and now we can sort them. And basically, in order to check that this grouping works, we just have to make sure that every every number is in the same group as its position. I think we got the code. We really got the code. Let's do it. Upstream time. Alright, now we gotta make our n and our m, and then we gotta store all this nonsense. So int m, I can't speak, and then int position, or we gotta say p, and then 1001, let's say. And then we got all our wormholes. How are we gonna store that nonsense? Alright, we're gonna do it my epic way of a bunch of pairs. So we're gonna do pair of an int, because we want to sort it by weight, so we'll put that first, and then int. And then this will be wormhole. Okay. Alright, now we read everything in. Cool. Oh wait, we need to make this an array. Hold up. So 1001. Alright, so we read everything in, and now we gotta sort our wormholes in order, okay? So what we're gonna do is we are going to, what are we gonna do? We're gonna sort. So we need algorithm. Sort wolf plus m, okay? And then what we gotta do is we gotta go from the end and we gotta go backwards. And we need to figure out our union find nonsense. So the way we're gonna do union find is we're basically gonna keep track of, what are we gonna keep track of? Let's just do like quick find. So the way we're gonna do that is we are going to make an array with 1001 numbers, and that's basically gonna tell us which group each one is in. This is not how you do things in C++. Okay, wait. Int group. Okay. And then we're going to make a method to combine two things. So basically at the very beginning, we should make sure that like our groupings are all equal to themselves. So they're all in a group by themselves. So for int I is equal to, actually we can literally just do it in this one over here. So here we can say group I is equal to I. Alright, and then we'll make our union thing. So it'll be public void, or we just don't need public void union. And then we'll pass in our first group, and we'll pass in our second group, and we basically gotta combine these two. Oh no, union's a thing. Union, combine. Let's say just combine. Okay. So we're basically gonna take int gx, which is the group of x, so we'll take that, and then we'll have the group of y. And then we'll take everything that's in group y and put it into group x. So we loop through our array, and then we set everything that was originally y to x. And then we also want to check if they're in the same group. So the way we're going to do that is we're literally just going to bool same or in group, or what do you say? What do we just call it? Find. Okay, int x comma int y, and then we'll just return group x equal group 1. Noisu! Okay, so basically this is going to sort it from least to greatest. So we gotta go from greatest to least. So what we're gonna do is we're gonna do epic reverse for loop, okay? Alright, we didn't screw up the reverse for loop like I always do, that's pretty good. And basically what we're gonna do is, wait, we should first check if it works in the beginning. So why don't we have a validate thing? Yeah, why don't we have a validate thing to check if the current grouping works? Okay, so bool validate, and then we don't need to pass in anything because we're just going to use the current group. So the current grouping means that everybody's in their own group. So basically what we're going to say is that each thing has to be in a group with its index. So basically if our p of 0 is equal to 3, that means 0 has to be in the same group as 2 because we are shifting everything from 1 through n to 0 through n minus 1. Okay, so for int I equals 0, I less than n, I plus plus, we are basically going to check, oh, why don't we just pi minus minus every time? Pi minus minus. Okay, so now everything's shifted down, we don't need to worry about minuses anymore. Oh wait, no. Well, we also gotta shift this down then too. I hate this. Okay, should we? I don't want to use. I like indexing from 0 though. Okay, yeah, we're just gonna index from 0 and we're gonna make it work our way. Dude, why do we even have to start from 1 numbering stuff? God dang it. They should just make everything index from 0, but whatever. Now everything's indexed from 0. So if is not in the same group, so if I is not, or actually we have to do if find pi is not in the same group as its I, then we have to return false. However, if all of them are in groups with their index, then we are Gucci and we return true. Nice. That's not how you do it. So, and then before we do this stuff, just to make sure, so if validate right now works, then we just c out, or f out, -1. Alright, so then now we gotta combine the things that the wormhole connects. So, for the first one, or for every loop, we basically had to do combine wormhole I dot second dot first, wormhole I dot second dot second. And then we say if validate. If now it's valid, then we fetch the weight of the current wormhole, and then we return because we're done. And then at the very end, it should work, so then we should be good. Okay, let us try it. That was kind of fast, so I feel like I probably did it wrong, but we could check it out. Wormsword.in. Okay, guaranteed it. Oh, it didn't error. But it didn't print anything either, which is troll. Is there validate right? So if find pi, which should be the group of pi, or no, sorry, if pi, which is the index that it should be at, is not in the group, then it returns false. Please? Come on, yes? What? No. Hold up. Wait, I'm erroring out? God dang it, what am I doing? Wait, where am I erroring? So, oh. Wait, what? Oh, it's 10 to the 5. Wait, what? How did I think it was? Bruh! Whoops. Wait, what is the E though? How could I got? Wait, shoot, that actually ruins my whole algorithm. Well, no, if we do smart union find now, okay, I guess we had to do smart union find. God dang it. Wait, does it work? No, because if we run validate every time, that's not gonna work. Wait, bro, this is flawed in the first place. It wouldn't even work on that. Okay, let us think again. Well, basically, from the beginning, we know which ones have to be in which groups, but then how do we make sure we reach that point? So now we had to figure out how to do quick union, and we also got to figure out how to figure out whether it's done or not. I know our strategy from going from biggest to least for sure makes sense. Now, how do we figure out whether it works or not quickly? I know for a fact that it's connected component because that's how it works, right? And then if you go backward, that for sure makes sense. Then how do you like check whether it works quickly? So we had to be able to do that in log n time. Oh, bruh, god dang it. We've been doing it wrong the whole time. Wait. What happens if, instead of going through it one by one, because it's impossible to validate, what happens if we binary search on the answer, and then from there we decided our solution? Okay, so the reason why binary searching works here is because, like, if you put a number, then you can take anything above that, and if you increase it to some point, it'll stop working, and if you decrease it at some point, it'll start working. So that's why we could do binary search. And how would this work on this problem? So 3, 2, 1, 4. And then basically the way that it will work is, like, let's say that we choose 9 and above. Then we basically go through all the 9 and above wormholes and add them over here. Boom, boom. Okay. And then we can basically just use our union find thing here, and it doesn't have to be smart union find either. Or actually, it has to be quick union. Okay. Actually, wait, it doesn't even have to be, because basically all we gotta do is we gotta find connected components, which is probably just faster if we just DFS from each thing. So we find all the connected components, and then we want to make sure that each one is connected with its corresponding index. Okay. And then that'll take n time to find connected components, and then like log n time to binary search. So that should be fine. Let's just do that. Okay, so we don't need any of our union find. Oh, I was so excited. God dang it, I wanted to do union find. That's so sad. Okay, so we don't need all this nonsense. And we will basically have a binary search. So int low is equal to 0, int high is equal to 10 to the 9. So 1, 0, 0, 0. 0, 0, 0, 0. Okay. And then we got to sort still. Sort wolf comma wolf plus m. And then we'll have a validate thing separately. So validate our bool validate with w, okay, or wait, what the heck? No, int w, okay. And then basically it'll take all the wormholes above a certain point. So we got to do lower bound. So we're going to do, we'll do int index is equal to lower bound. And then we will do woof.begin, woof.end, and then we will put in w, 0, 0. So that means everything above it will work. Okay. Oh, it's not a vector, so we can just do woof and woof plus m. Okay. So we have this now, and basically, oops. And then basically what we want to do. Oh, wait, then we had to convert it to an int. Oh, wait, this should work. Okay. I think we had to do that. Okay. So now we have our index, and we basically had to add every single other pair as a edge, and then we will have something epic. So we will make an adjacency list here. So we will have a vector. We need to include vector, and then vector int adj. So how many do we have? For all int I equals index. I less than n, I plus plus, or I less than m, and then we'll add all the wormholes in. So adj, or actually let's say int x is equal to wormhole I dot second dot first, and then y is equal to second dot second. So x and y are the two things that the wormhole connects. Okay, and then what we're going to do is we're going to do adj x dot pushback y, and then the same thing for adj y. Okay, and now what we got to do is we got to DFS to find connected components. So we're going to first have our visited array. So we'll have our dual visited, or no, we had to have int visited because we also want to keep track of connected components. So int visited is equal to our 1001. And then we will set everything to -1. And then we basically BFS, DFS doesn't really matter, and we will set everything to the correct stuff. So int count is equal to 0, and then we'll have our q, so we'll include q. So we can do BFS, and then we'll have q int, q, and then we will q dot push 0. So it'll start at 0 and it'll BFS from there. Or actually, we need a for loop first. So for int I is equal to 0, I is less than n, I plus plus. So it's going to go through all of them and start a DFS from each thing that isn't visited. So if not visited, or if visited I is less than 0, then we will DFS from it. So we will push I, and then while our BFS is still going, while our queue is not empty, then we will keep going. So first thing we got to do is we got to take int x is equal to q dot front. Then we got to pop the q, and then we got to visited x, or actually we got to first check if x is visited. So if visited, actually why don't we just check if it's visited at the beginning. So if it's that, then we said visited is equal count. Okay, so we know that everything that's in the queue is going to be visited. So we gotta put things that are not visited into the queue. So for everything that's adjacent to x, we're going to put it in the queue, and we're going to set it as visited. Oh, we shouldn't use I again, so j. And then visited j is equal to true. Okay. Oh no, not true, we had to set it to count. And then once this is done, then we could count plus plus and very epic. Okay, so now we've DFS'd and we want to make sure that each thing is in the connected component with its index. So what we're going to do is we're going to do a for int I is equal to 0, I is less than n, I plus plus. If visited I is not equal to visited pi, then we are going to return false. However, if all of them are in the same group, then we return true. Okay, so now we have our validate, so now we could easily do our binary search. So, while low is less than high plus 1, oh no, high minus 1. No, actually, yeah, minus 1, that's how I like to do it. Then if validate, actually we'll make a mid. Int mid is equal to low plus high over 2. If validate mid, in which case it works, then we could go higher. So then we set in low equal to mid. However, if it's not true, or actually we're gonna say else, then we could set high to mid, or mid plus 1. Okay, and then we should see out low at the end. Okay, let us test it. Probably not gonna work the first time because we always get errors, but we shall see. Noise negative. Wait, what? How did it get negative 1? Oh. What's wrong with my lower bound? Oh, does it need to be in a vector? Okay, why don't we just make it a vector then? Oh, here, maybe. If visited j, if not visited, less than 0, then we could do this. Anything else, troll? Oh, bro, I don't pop the Q, god dang it. Very good errors, must say. Try it again. Okay. So basically the problem is now that it's always validating as true. Oh, that makes so much more sense, okay. Oh, so it might be working. Okay, let's test it with the thing. Okay, this is with the normal one. Okay, let's see. Hold up. Okay, so let's try that. Okay, that's how you do it. Okay, so that's how it's supposed to work. Okay, and then we also have to make sure that the max. Okay, so we'll keep track of the max weight, and if our W is greater than the max weight, then we are done. Okay. Int max weight is equal to 0, and then max weight is equal to max of max weight, comma, woof I dot first. Okay. And then at the very end, let's make this one more bigger, and then if, oh, what, did one more bigger not work? Let's see, 2, let's make this 2. Okay, and then if max, if our, if the thing that we found is low is greater than max weight, then we just return cout negative 1, otherwise, we do the other thing. Okay, this should work, let us test this. Wait a minute, what? Why did it randomly time out on 2? Okay, so, I'm assuming that's the case where it's negative 1, so maybe that's too big. So how many zeros do we have? 3, 6, 9. Oh, maybe we should just set this to max weight plus 1. Okay, that probably is the problem. Okay, let's see. Wait, what? Oh, we should make a max weight plus 2 just so that it doesn't troll too hard. Okay. Yeah, because the problem is that low is going to be equal to max weight, so it won't be greater than max weight, so it won't return negative 1. So it has to be max weight plus 2. Okay, this should work. Alright, we did it. Let's go. Finally, let's do it. Okay, so basically, the thing to learn from that one is that sometimes you could completely think of the wrong solution, and you might think it's right, and if you code it too fast, it's a waste of your time. So you should work out the entire solution before you start coding. Also, another thing that I was not very smart about is when I was trying to think of the solution after, I kept fixating on my initial solution, which is not a good idea. So, be willing to think, completely restart your thinking in order to come up with a solution. It took me a while to come up with a second solution, but we did it. Okay. Alrighty, thank you guys for watching. Please give me suggestions for what AP Crash Course videos you guys want to see, because those are coming up soon, okay? Don't worry, I will get to the US Open review. That will happen once the results are out. Alright, as always, if you enjoyed the video, leave a like and subscribe for more. Thank you guys for watching so much, and see you guys next time.